What happens to your next meal if you never needed to eat it? Right now, every calorie in your body came from something you consumed, chewed, and digested. But what if your skin could do what a leaf does? What if sunlight alone could keep you alive?
It sounds like the ultimate biological upgrade. No hunger, no grocery bills, no farming. Just stand outside for a few hours and you're fed. But the actual biology of turning a human into a photosynthetic organism reveals something far stranger than a convenient shortcut.
Let's start with the energy math, because this is where the idea runs into trouble almost immediately. Photosynthesis converts sunlight into chemical energy using chlorophyll, the pigment that gives plants their green color.
On a clear day, the sun delivers roughly 1,000 watts of energy per square meter to the Earth's surface. But plants are remarkably inefficient at capturing it. Most plants convert only about 1 to 2% of that available sunlight into usable chemical energy. Even under ideal laboratory conditions, the theoretical maximum efficiency tops out around 11%. Now, compare that to what a human body actually needs. The average adult requires roughly 2,000 calories a day just to maintain basic function, which converts to about 2.3 kilowatt hours of energy. To capture that much energy through photosynthesis at a generous 2% efficiency, you would need to expose approximately 40 to 50 square meters of photosynthetic surface to direct sunlight for the entire daylight period every single day. For reference, the total surface area of an average human body is about 1.8 square meters. Even if your entire body were covered edge to edge in chlorophyll, you would be capturing less than 5% of your daily caloric needs. You wouldn't need to stand outside for a few hours. You would need to lie flat in direct sunlight for the entire day, and you would still be running a massive caloric deficit. So the math alone rules out photosynthesis as a replacement for eating. But let's say evolution found a workaround. Some hybrid system where photosynthesis supplements rather than replaces digestion. What would your body actually need to change? The first problem is skin structure. Plant cells contain chloroplasts, specialized organelles packed with chlorophyll, arranged in leaves that maximize surface area while staying thin enough for light to penetrate deeply into the tissue. Human skin is built for an entirely different job: protection. It's thick, layered, and populated with structures that have nothing to do with capturing light. Hair follicles, sweat glands, blood vessels, nerve endings, and a dense protein called keratin that actually blocks a significant portion of incoming UV and visible light before it can reach deeper layers. For photosynthesis to work efficiently, human skin would need to become thinner and more translucent, which immediately creates a new problem. Skin's thickness is what protects us from infection, dehydration, and physical damage. A translucent, leaf-like epidermis would leave humans radically more vulnerable to the environment, trading caloric efficiency for a massive increase in mortality risk from cuts, infections, and moisture loss. Then there's pigmentation. Chlorophyll is fundamentally a light-absorbing molecule, meaning photosynthetic skin would need to be green, or close to it, across most of its surface. Human skin already produces melanin, partly as protection against UV radiation damage. A hypothetical chlorophyll-based skin would need to balance two competing jobs: absorbing enough light to be useful,
while somehow still protecting the DNA in skin cells from the same radiation that photosynthesis depends on. Plants solve this with waxy protective cuticles and by sacrificing individual leaf cells regularly. Humans, with a much longer lifespan per cell generation, don't have that luxury. And here's a detail most people don't consider. Some photosynthetic organisms already exist inside animals. In 2010, researchers led by Sidney Tamm confirmed that the spotted salamander hosts a genuine symbiotic algae living inside its cells, including inside developing embryos. This remains the only confirmed case of a vertebrate incorporating photosynthetic organisms directly into its living tissue. It's not the salamander's own cells performing photosynthesis. It's a permanent algal roommate doing the work and sharing a portion of the benefit. That distinction matters because it points toward the only biologically plausible path for human photosynthesis. Not human cells evolving chlorophyll from scratch, but a symbiotic relationship, similar to what already exists in coral reefs, where coral polyps host photosynthetic algae inside their tissue, receiving a meaningful portion of their energy needs directly from their photosynthetic partners. If humans developed something similar, evolution would likely favor a partnership, not a redesign. Specialized skin cells hosting algae colonies, providing a caloric supplement, not a replacement. Even then, given the surface area limitations we calculated earlier, that supplement would realistically cover a small percentage of daily energy needs, enough to reduce hunger slightly during long periods of sun exposure, not enough to skip meals entirely. So, what would society actually look like with this modest photosynthetic boost? Sun exposure would become a genuine biological resource, not just a source of vitamin D. Wealth and geography would matter in new ways. Equatorial regions with consistent, intense sunlight would offer a real caloric advantage over cloudy, high-latitude regions. Indoor workers and people in sun-scarce climates would need proportionally more food to compensate, creating an entirely new axis of nutritional inequality tied to something as simple as where you live and how much time you spend outdoors. We didn't evolve chlorophyll. We evolved something else instead. Complex digestive systems capable of extracting far more energy from a small plate of food than 50 square meters of skin could ever pull from the sun in a full day. Maybe that wasn't the missed opportunity it first appears to be. Maybe eating was always the more efficient design.